All right, friends, here it is, the big day where I make sure I've explicitly said what this rule for derivatives is that we've been kind of dancing around. Here is a summary of some work that we've done over the last few weeks. On the left side, you see a bunch of functions you worked with. On the right side, you see a bunch of derivatives that you had figured out by using that whole crazy definition in Wolfram Alpha and simplifying stuff. And the pattern that exists that hopefully I can get you to see right now if you haven't before is whatever the original function was, you can find its derivative by doing something with the exponents and the coefficients. There's a relationship there that just happens to be the case. There's no reason why this has to be true. It just happens to work out. And here's what it is. If you haven't seen it before, here's what I'll say. This very first function, this term kind of corresponds with this first term. And this second term, whoops, I wanted to change colors there, corresponds with the second term of the other one. And even though there's like this term actually corresponds with the fact that there's nothing else left. And I'm gonna go through all of these things and just circle the things that correspond just to really try. Now, if you already know what the pattern is that I'm talking about and you're, seeing this, you can skip the rest of this video probably and move on to the next ones. But if you haven't seen it yet, I really wanna just draw this all the way out. That corresponds with 0. This guy ends up being related to this dude. This dude is related to this dude. This is related to this. And this guy is related to the fact that there's like a plus 0 at the end. So if you haven't seen it, pause the video for a moment, look at the exponents, look at the coefficients, see if you can't see what the pattern is, and then when you think you have it, press play, and we'll see if we agree. So now that you've thought about it, and you've had a chance to see it, what's basically happening is for all cases, we're taking the exponent and multiplying it by the coefficient to get the new coefficient, and then we're decreasing the exponent by 1. For example, let's start with this k. It's easiest to see it with this k. I had a 2x to the 5th, and I'm saying that corresponds to the 10x to the 4th. And that's because if I were to multiply the power by the coefficient, 5 times 2, that gives me that brand new coefficient. And then of course, if I decrease this power by 1, that gives me the 4. So the power times the coefficient gives a new coefficient, and decrease the power by 1. We see it over and over and over again, right? This right here, the negative x cubed, that ends up corresponding to this negative 3x squared. There's like a 1 in front of here. So this power times this coefficient makes the new coefficient. And if I decrease that power by 1, that's the new power. So that's like the basic thing that's gonna work for everything I've given you so far, actually. There's some weird things that happen that we're gonna talk about in the other slides. But that's really well illustrated on this particular, all of these green functions that I'm sharing with you. I do want to talk for a brief moment about how the dark purple stuff doesn't really break the rule at all. The rule being that the power times the coefficient is the new coefficient. Oh, I should write this. I'll write it down in the next slide. And then we decrease the power by 1. What I want you to think about is this. When we have something like this negative 2 here, which I'll write in light blue so we can see it. That negative 2 is, bear with me, the same thing, there's no x's on there, right? No x's at all. We do know that if you take anything and raise it to the 0 power, anything to the 0 power equals 1. So I'll say that x to the 0 power specifically definitely equals 1. So I can think of this as having like x to this power on it, and I haven't really changed its value at all. It's still negative 2. And then we can kind of see why that negative 2 is going to correspond to like a 0 in the derivative, which I, of course, would never write plus 0. Who does that? It's a waste of ink. But the rule applies. If I take this power times this coefficient, I get a new coefficient of 0. And then I would decrease that power by 1. But honestly, so I'd have, 0 over x? That's still going to be 0. So we just don't write it. So every single time we have a term that doesn't have an x on it at all, and we go to take its derivative, that term that's a constant just disappears. So take a good solid look at all these places where this pattern exists. When you feel like you really understand it and are comfortable, this corresponds to this corresponds to this guy, This corresponds to this guy. Let's look at some other things that happened over the course of the last 6 weeks where it seems like the rule maybe doesn't apply, but it totally does. It's gonna be fan-freaking-tastic. All right, we'll see you in the next slide, my friends.